Good day, folks. Here's another video of the work energy and power on an incline. It says a box is held stationary at point A. That means the initial velocity is 0. The top of the plane ABC inclined to the horizontal. The portion AB plane is smooth. That means no friction. So this AB, there's no friction, while the portion BC is rough. That means there's a friction. Now, what they say here, this object of mass, but we are not given the mass, it's at rest. That means it would reach point B with the final velocity that we do not know. And this is what? Smooth, frictionless. Frictionless. So meaning the only force that is acting there is the gravitational force, Fg parallel, right? So there's no other force. So this is a what? This is a closed system, which is A to B, it's a closed system, right? And then B to C, it's a what? It's an open system. Now 4.1, and this object is in a height, and if you're going to look at the system, we're going to look at this only. We'll take this as a ground. If you're paying attention there, we're going to take this as a ground, right? Now, the 4.1, it says state the conservation of mechanical energy. The conservation of mechanical energy, it says the total mechanical energy in an isolated system remains constant. So this is an isolated system. This portion AB is an isolated system. The mechanical energy here is equivalent to the mechanical energy here. In fact, the mechanical energy all the way to B is equivalent, as constant. Now 4.2, it says calculate the speed of the box at B. So the speed of the box at B, we're going to use the conservation of mechanical energy to calculate that. So let's cut the chase. 4.2 will say mechanical energy at A is equivalent to the mechanical energy at B. So the formula there, it's mgh initial plus half mv initial square equal to mgh final plus half mv final square. So since we are not given the mass yet, the masses cancel there. So we'll work without masses. So it's going to be 9.8 times the height. The height is 0.5 plus the initial velocity there is 0. So this is going to be 0. And it's 9.8. The height final. The height final is going to be 0. So with times by 0, it's going to be 0. And then half the final velocity, that's the one that we want. So here we're going to have 9.8 times half is going to be 4.9 this side, and we're going to have half here, VF square. So when you put that in the square root, it's going to be 3,13 meter per second. Right, we're done with that. I hope that makes sense. Now they say in 4.3, the box experiences the kinetic frictional force of 14.7 as it moves at constant velocity from B to C. So here it has a frictional force of 14.7 and it moves at constant velocity. So the speed that it has here, which is the speed that we just calculated, it reaches this point by a velocity of 3,13, and it's 3,13 all the way because it's constant and there's a frictional force and the gravitational force there. Now it says state the work energy theorem. The work energy theorem, guys, it says the net work done on an object is equal to the change in kinetic energy of an object. Now 4.3.2, it says draw the free body diagram showing all the forces acting on the block at B. So it's 4.3.2, drawing the free body diagram there. So it's at an incline, guys. Remember, the free body diagram, no components needs to be involved. There's a normal force, there's an FG, and there is how is it inclined? The normal force is not like that, guys, sorry. The incline is not like that, it's the other way around. The incline is this way, so we have the normal force and the gravitational force and the frictional force, right? The frictional force, right? That's your free body diagram. So you do not show the FG parallel and FG perpendicular, guys, you're going to be wrong. It's no longer allowed this year. So it says use work energy principle to calculate the distance between B and C if the box has a mass of 3 kg. Now we're given the mass, so we want this displacement, which is D. So they said we should use work energy theorem. So using work energy theorem, it says work net is equal to change in EK. Since it has a constant velocity, the change in kinetic energy will be 0. So what are the forces that are acting there? It's the work done by friction plus the work done by FG parallel. So what are we going to do there? So the work done by friction is going to be FK. FK change in X cos theta, and then the gravitational force, work done by gravitational force, it's going to be negative change in P, which is it's M negative mgh final minus mgh initial. So it's going to be mgh final minus mgh initial equal to 0. And then we substitute the friction, it's 14,7, and the displacement is D, and then cos 180 degrees, and the mass is 3 times 9.8. Height final is 0, and the height initial. So at B, the height is what? Is 1. So the height is 1, and then so here we're going to have negative 14.7 D, and then here we're going to have 29.4 equal to 0. And when you put in that side and you do your math, your D is going to be 2 meters there. Now the last question, it says the angle between the incline and the horizontal decreased. So the incline here, it has decreased, it's like this now. Now it says how will the decrease affect the coefficient of kinetic friction acting on the box? Always, guys, if the angle is changed, the force has changed, the coefficient of kinetic friction will remain the same, because the kinetic friction, the coefficient of kinetic friction remain the same because it depends on the type of surface or the type of material.